Okay, let's calculate the normalized relative point density. This is used to calculate the density of an understory in a point cloud from LiDAR. This is in comparison to the ordinary relative point density, which really just factors out the overstory from this metric and really just compares the density of points in an understory to all of the points in that understory and below, effectively canceling out the energy absorption by the overstory. Formula for this is pretty simple. Just count the number of points between some height band, as for instance between 0.25 and 2 meters, and then divide that by all of the points from 0 to that upper limit, in this case 2 meters. So the steps that we're going to take to do this, we're actually going to produce a density raster. So we're going to be calculating density at a bunch of different grid cells. And so to do this, we're going to start by classifying ground in the point cloud, unless that's already been done. And in the example that I'll be giving, that has already been done. So this is going to be a data set that was processed in DJI Terra, and those values are supplied. We're going to calculate a canopy height model in CloudCompare. There's lots of ways to do this. You could use LazTools or PDAL or ArcGIS, but it's nice to visualize the problem in CloudCompare, and CloudCompare can solve this problem pretty easily. We're going to separate out the two clouds in CloudCompare that we're interested in. One, that top understory layer, in this case from 0.25 to 2 meters, and then everything between sort of the bottom all the way up to that 2 meters. And then we're going to calculate the density. So we're going to calculate the density for the top. We're going to calculate the density for all, and by all I just mean that 2 meters and below. We're going to calculate the density, the top divided by all, and then fill any voids that we have with 0. This is what that looks like in ArcGIS. So this is the point cloud that we're going to be working with. This was captured with the Matrice 350 and the L2 LiDAR, just at the beginning of kind of the fall season, so you can see the trees starting to turn. And we're going to subsample this. You could do it for the whole cloud if you wanted to, but we're just going to take a little slice for the purposes of this example. So we're using our extract tool and extract that little piece. And here we are. Very pretty. You can look at the bottom of this and see the density of the ground surface. And if we, in CloudCompare, look at the scalar field, we can see the ground classification that's been done again in Terra. So a nicely classified ground layer and then the stuff above it. So the first thing that we're going to do is we're going to split off that ground layer. So CloudCompare has some good tools for doing this, and I'll just mention if you needed to do the ground classification, you could also do that in CloudCompare with the class simulation filter. You could manually mark this up if you wanted to. The results aren't all that sensitive, so it really wouldn't hurt anything. So here's the CSF filter, and to do the manual filter, you could just use the scissors tool, which is a segmenting tool, and I'm just going to really super roughly segment this, just imagining. Now you do this, in reality you do this much more precisely, but just as proof of concept you could do this and then click on the pound sign there to assign the value of, in this case, 2 to those values. I'm not going to do that. It's just for an example, but and of course many other algorithms that you can use to classify that ground. But my ground layer is already pre-classified, so I don't need to do any of that. I can just kind of continue on. So what I'll do here is go up to Edit and go into Scalar Fields, and we're just going to do a simple split cloud by integer values. That's going to give me a cloud for the ground layer, number 2, and the ground layer 1, which is everything else. I don't really care about the everything else. All I really cared about is the ground layer. So here it is. And then you can see that it's got some holes in it, tree trunks and this and that. So the next thing to do is to transform that into a mesh. So we'll go to Tools and Projection. Just got to make sure that cloud is selected. And rasterize. Now we're not actually going to produce a raster here. We're just going to produce a ground layer. We're going to use the median to do it. I'm setting the step size, which is at the top at 1. I'm going to fill empty cells with kriging. And ultimately, I'm going to create a mesh here. But what I want to do is make sure that I have a good-looking mesh here that seems to represent the ground surface. Looks good to me. So the next step is to classify the cloud to mesh distance. So that's a tool right here. Now this should essentially put these things in the right order. The mesh is going to be the reference. That's what we're measuring from. Keep those signed distances. You're going to want these. And then we'll first compute. Now this may take a little while to run, so we'll jump ahead to the next phase here. So we've jumped ahead to 98% done. If we wait just a moment, that will kind of lock in. The OK button will become ungrade, and we can basically apply that calculation back to the point cloud. At this point, you can turn off your ground surface and your mesh. We don't really need those anymore. But the original point cloud then has the C2M signed distances, and so the scalar value that we're visualizing here is the height above ground. And you can see the peak there down at the bottom that represents the ground surface at 0. We've got a lot of trees above it, so you can see that in the histogram. And you can, if you look, you'll see that these values go down to negative 7.74. So we do have some of these points below the point cloud, below the mesh. In fact, that's not so surprising. We used the median, we used kriging, and so we do have some values that are below that. If you really wanted to avoid that, you could use the minimum, but it doesn't really matter here. We'll just take note of the fact that we do have some negative values. And then make sure we're keeping track of that when we do our calculations down the line. So this is the construction of a canopy height model, and now we can proceed to the next step. Okay, so we have our canopy height model, and the next step is to isolate our understory layer, and basically the top of the understory all the way down from there, which I'm going to call all. Both of these are sort of discounting the overstory. And this comes from a paper. This figure and this text comes from the Campbell et al. Paper from 2018 linked here. Just basically describing the formula for NRD, the number of points within that understory divided by the number of points and the upper limit of that understory down below, so less than 2 meters. So that's what we're going to implement in CloudCompare. We've got our canopy height model. The coloring that we have here, it's a little hard to tell, but the coloring here is related to the height above ground that we calculated in the last step. If you look at the bottom here, we've got a relatively good ground layer. The variable that we're looking for here is the C2M signed distances. And we do have some negative values because we used a median, sort of a median fit and kriging. So basically what we need to do is go to scalar fields and filter by value. And we're going to set this upper limit, in this case, to 2 meters. That's what Campbell did in their paper. So you may have to adjust that 2 meters to whatever you're interested in. But then we just export export that out. Here we go. And that's everything below 2 meters in our data set in the canopy height model. And this is really interesting. You can see the kind of stripes running through here that are related to higher densities, probably directly below the instrument as it was flying. So a higher density return pattern. And that's basically what we need to factor out. So we're interested in sort of the other stuff that's above the surface there, the brush, the trees, things like that. And so we're just going to split those off as well. So here we're going to go to Edit, Scalar Fields, Filter by Value again, except this time we're only going to be looking at things from a 1/4 meter up to that 2 meter top. So we're going to export this back out again. And there you can see, really just the trees and the understory, and not those ground returns, or at least as few of them as we can manage. And then what we have to do is just save those out. So we're going to basically save those. Go File, Save As. We're going to save this as an LAS file. We're going to save everything from that 1/4 meter to 2 as top.las. We're going to be doing the rest of the work in Arc, so it's kind of important that we keep this in LAS and not LAZ. We're going to save everything from 2 meters on down to all.las. And then when this is done, we can, in ArcGIS, just drag those layers back in. Great. And with that done, we can then do the next step. So we'll move on to that. Okay, so what we can do now is calculate the densities for these. We're going to be using a tool called LAS Point Statistics as raster. So here I'm just selecting the top layer and making sure to change the method to point count and setting the sampling value to 1. That's 1 meter because my input data is in meters. And then I'm going to do the same thing for all. So these are very quick calculations, and you can compare these two surfaces. You can see the differences in collection and how those affected the result. And so here we're just going to divide the one by the other to calculate the overall density. So the top divided by all. And when you do that, you'll notice that we have a lot of voids. There are a lot of places where there weren't values. And when we do the division, that clearly doesn't work out. So to fill those values, we'll just use the conditional tool. So that's con. And sort of a strange phrasing here, but we're going to look for cells where the value is null. And then where they are null, we're going to set a constant value of 0. Otherwise, we're going to use the value that's there. So we'll hit run here. And now all those empty cells are filled with the zeros that we need. We'll change the symbology back so it looks a little bit better. And now we get a nice view of the overall understory density. You can export this raster out. I won't demonstrate that. That's easy enough. You could apply smoothing. You could do a bunch of other things to this. But this is a good overall metric. Hopefully that's helpful. And be in touch if you have any questions.